Let's look at the similarities between flow of heat and flow of electrical currents and see how we can use such similarities for solving the 1D steady state heat conduction problems. And to do that, I'm just going to give an overview of Ohm laws for the electrical flow. So what we know for electricity flow is to So what we know for electricity is the electricity flow or current is the potential difference divided by the electrical resistance. So let's say if we have a circuit here, and we have a delta V, let's say here is V1, V2, and this is R. Now the electrical current that passing through this circuit I is going to be 2 delta V divided by R. That's for electricity. Similarly, if we have a, let's say, laminar flow in a pipe, we have exactly similar situation. Let's say I have this pipe. There is a flow rate going in, and we have a delta P here, the pressure difference. For a pipe with a diameter of D, we can write Q is equal to delta P divided by 32 mu L pi D4. Or another way, this delta P is P1 minus P2. Is the difference between the pressure difference across the pipe that we have, P1 minus P2, divided by some values that depends on the pipe geometry, length, diameter, and the viscosity of the fluid, which causes a resistance. So the smaller the denominator that we have, like smaller viscosity, we have higher flow rate. Larger pipe diameter, we have for the same delta P, we have a larger flow rate that can exist. Now, if we look at heat conduction flow or Fourier's law, what we have is flow rate Q is equal to we can write the heat flow rate as a temperature difference, delta T, and something we call the thermal resistance or RF, or resistance of thermal, RTH. Now, this is flow rate of thermal energy. Based on Fourier's law, Q is minus Ka T2 minus T1 divided by delta X. And this is for a simple geometry where we have, let's say, T1, T2, this is delta X, and this is Q. which is equal to T1 minus T2 divided by delta X divided by Ka. So you would see that this delta X divided by Ka that we are writing is the thermal resistance or what we define as RTH. Based on this thermal resistance, if let's say K is small, or as a poor conductor, then this resistance RTH is large, which makes sense. We have a poor conductor here. So we can view the conduction equation equation delta T divided by RTH. Now, if we go back to the multi-layered composite wall, or composite wall that we had, just gonna briefly sketch one example of that. Let's say this is material A, Ka, material B, Ke, V, Kc, A, and so on. So what this is Q, we can just treat them similar to the electrical resistance, and we can say, you know, we have temperature difference that provides the potential T1 and T2, and then treat each of these layers as a resistance. So here is T1, here is T2, and then we have this Q, which is heat flow rate, and this one is RTH1, RTH2, RTH3. So this is electrical analogy for composite, where each of these R's, let's say RTH1 is delta XA Ka times area. And similarly for RTH2, RTH3, if I want to go by this analogy, then what we have here is this delta V1 is equal to I RTH1, or yeah, RTH1 delta V2. Let's make this one delta T so it's more clear here. Delta V1 IR1, delta V2 IR2, and delta V3 is IR3. So I'm just considering, let's say there is a potential between each of them. Or equivalently, For the heat, what we have is delta T1 is IRTH1, delta T2 IRTH2, delta T3 is IRTH3. So let me just put it here, delta T1, delta T2, delta T3. And we can get similar resistance that we had and the similar heat flow rate that we got previously. Similarly, we can use it for the Newton's law of cooling. If you recall, in Newton's law of cooling, Q was heat transfer coefficient, area T of surface minus T of infinity, which I'm gonna treat it HA delta T, or in other words, what we can write is Q equal to delta T divided by 1 over HA. And comparing with what we have here, the thermal resistance when we have convection or Newton's cooling law is going to be 1 over HA. So in summary, this resistance to the thermal for the conduction is going to be delta X Ka, where K is the thermal conductivity of the materials that we are looking at, and delta X is the thickness. And for RT of convection, this is going to be 1 over HE. What's the unit of that? What you're getting in terms of unit is going to be Kelvin per watt.